Okay, so this is chapter 14 homework. All right. So first one, a stationary boat pop, bobs up and down with a period of 2.3 seconds. So we know period equal to 2.3 seconds. Okay. When it encounters the wave from a moving boat. Okay. All right. So what is the frequency of the wave? So this is about a wave. So frequency equal to 1 over period. Okay, so that's a frequency. So just plug in and you can figure this out. In the unit of hertz. Second one, if the crests of the wave are 8.5 meter apart. So crest means, you see, this is a crest. Okay, so this is a crest, this is a crest. So this is 8.5, all right, which means wavelength is 8.5 meter apart. What is the speed of wave? Speed of wave always equal to wavelength times frequency or wavelength over period. Okay, so plug in. So actually, from equation, right? So let's use period and wavelength, right? So wavelength 8.5, period here is 2.3. Okay, so that'll be the speed of wave in the unit of meter per second. All right, so that's the first one. Second one, a 4.5 hertz wave with an amplitude of 12 centimeters. So here we know frequency equal to 4.5 hertz, amplitude A equal to 0.12 meter. Okay, so centimeter turn to meter, and a wavelength lambda equal to 0.27 meter. Travels along a stretched horizontal string. All right, so that's what we have: frequency, amplitude, and wavelength. How far does a given peak on the wave travel in a time interval of 0.5 seconds? So t equal to 0.5 seconds. All right, so that's what we need to know. So given time, how long travel? Well, this one is very easy to deal with. So because we know, if you know frequency, amplitude, and wavelength, we know speed of wave equal to frequency times wavelength, right? So this equal to 45 times 0.27. That's a speed in terms of meter per second. Okay, and talk about given peak. Any given peak, right? So you see here is a peak. So this peak, right? So this peak will travel in this direction with a speed of this. So give you time. So the distance, right, travel by speed over time, right? So speed is this one, and whatever time is this. So put together, that's the peak travel. So this one travel. Second one is how far does a knot on the string travel in the same time interval? Okay, so here is a little bit trick. So knot, here's a string. So you have a knot, those knot right on the string. So you look at this guy. This guy actually move up and down, right? You see that? So this is this guy's travel, just up and down. So we think this time interval, how much it travels. So in this one is pretty hard. So how to figure this out? The direct way is you have to write out wave function. So we know wave function is yxt equal to a cosine 2 pi lambda x minus 2 pi t. Okay, so here's what we have, right? And ask you about the knot, right? So any knot, the knot travel, right, is up and down. For the given knot, which means x is set to a given location. Well, how about let's use the x equals 0. Again, let's choose x equals 0 location, okay? So you see y, then you look at the t, right? So in terms of a t, x is set, right? Just like let me think. So you can use x equal to 0 or x equal to whatever location, just like 1 meter, okay? To make life easier, let's use 0, right? So this will be negative, so 0, right? So this the first one is gone. 2 pi over t. Okay, so that is the equation, displacement of the knot, right? And then so first you have to figure out what the t is, right? So the period, so period equal to 1 over frequency. So you have a frequency, then you can figure out the period, right? So so you plug into this equation. So this one equal to basically is negative 2 pi ft, right? Okay. So now let's see. Actually, it's why no. Oh, wrong. I make a mistake. I forget a cosine. So this guy is gone, right? So you have to put a cosine. Okay, so let me correct that. Okay, so equal to a cosine, right? Okay, so this is the equation. So now what's the t? T is 0.5. Okay, that's actually the time difference, right? So you can tell, you can give t naught initial time equal to, let's make a t naught equal to 0. Then what is t? Equal to 0.5 seconds, right? All right, so you can plug into this equation. When t equal to 0, then what is y1, right? So plug t equal to 0 here. So a cosine 0, cosine 0 equal to 1, right? So a is 0.12 meter. Okay, so this is a y1. Then y2 equal to a cosine negative 2 pi f is 45, okay, and then t, right, 0.50. Okay, so plug everything into this equation, plug in, and whatever it is. So a is 0.12, right? And let me make calculation. So this is 2 pi 45.5. Okay, it's a 4.5, not 4.5. Okay. So what we have here is, anyway, just like plug everything in, right? So you have a value. So whatever value. Let me see what is the value. Okay, let me use my calculator. So 4.5 times 0.5 times 2 times pi, right? And then you have to do cosine. One more time. A. Okay, let me see. Okay, oh my God, I get this 0. All right, so you see, When time equal to 0, when time equal to 1, when time equal to 0, right? It started with the 0.12. Then time equal to 0.5. This guy go to 0. So the distance traveled, how far? Well, this is 1 amplitude away. Okay, so that's an interesting question. Okay, well, so that's what I got. Well, that's what I calculated this. 2 pi 4.5 4.5 times 0.5 times 2. Yeah, 4.5 pi. 4.5 pi is 0. Cosine 4.5 pi is 0. Okay, yeah, that's 0. Okay, so that's distance traveled. How far? Well, now how far? This is how far I travel. Okay. All right, number 3. A brother and a sister trying to communicate with a string tied together, a time between 2 thin cans as shown in the figure. If the string is 7.6 meter long, has a mass of 29 G, and is pulled taut with tension. So there's tension, Newton, okay, and how much time does it take for a wave to travel from one end of the string to the other? Okay, all right. Looking for time, right? Looking for time. Okay, and well, to find the time, you know the distance. This is distance travel, right? 7.6. So time equal to distance over speed. You have to figure out speed of wave, right? So what's the speed of wave? Speed of wave equal to, for the given string, speed of wave set is tension over linear mass. Okay, so we know tension is given. What's linear mass? Mass per unit length, right? So linear mass equal to total mass over length. Okay, so you see this is 29 gram, 0.029 kilogram over length, 7.6 meter. So what's linear mass, right? So you plug into this equation, right? So this equal to 18 over 0.029 over 7.6. All right, so this equals square root of 18 times 7.6 divided by 0.029. All right, so that's the speed. And then you plug into, right? So 7.6. Okay, and then divided by speed, right? Divided by the thing. Okay, so this will be the answer. Whatever answer it is. Okay, so that's how far travel. How long it take? Just put it here. All right, next one. Number 4. 2 steel guitar string has the same length. Okay, string have same length, right? So this is L1, L2. Okay, and string A. Okay, string A, string B. String A has a diameter dA equal to 0.50 millimeter. Okay. Under TA equal to 410 tension. String B has a diameter of dB equal to 1.0 millimeter, has under a tension of TB equal to 820 Newton. All right, so from this relationship we know dB equal to 2dA and TB equal to 2TA. Find the ratio of the speed, right? So we know speed of the wave V equal to tension over linear mass. Okay, you see steel guitar, same material, right? So what's linear mass? So mu equal to total mass divided by length. Okay, and the length is the same. What's the mass? Mass equal to density times volume. Okay, volume divided by length, right? So density is the same because they are both steel. So what's the volume? Volume equal to pi area, right? Area times length. Okay, so volume. Okay, so pi d over 2 square. You see, that is radius square. Diameter divided by 2 is radius, right? Times L. This is the volume divided by length. You see, length cancelled. So this one equal to rho pi d over 2 square. All right. So plug into this equation. We know speed of wave equal to tension over linear mass here, right? Rho pi d over 2 square. Okay, so we know VA equal to TA rho pi dA over 2 square, right? And VB equal to TB over rho pi dB over 2 square. Okay, so VA over VB, you do the ratio, right? And you cancel the same part, actually 2 and 2 cancelled, right? So this equal to square root of TA over dB square divided by TB over dA square, TB over dB square. Okay, cancel the common part. All right, so this actually equal to square root of TA over TB dB square over dB square over dA square, right? So TA over TB is, so this is, from here is 1/2, okay? 1/2, right, square root. dB over dA equal to 2, right? So dB square over dA square is 2 to the power of 2, right? So this is, you see, half, 4, 2, square root of 2. So the answer should be square root of 2. All right, so that is your 4. Okay, keep going. Five. Okay, 5. Consider a harmonic wave with the following wave function. So this wave function, super important. Okay, so this wave, right? What is the least amount of time required for a given point on this wave to move from y equal to 0 to y equal to 12? Okay, so from this, what do we know? We know, so we have to turn that into standard form. 12 centimeter, right? Cosine 2 pi over 9 centimeter x minus 2 pi over 32 seconds t. You have to make a 2 pi over something. So from this, we can tell wavelength equal to 9 centimeter. That's wavelength. Period equal to 32 seconds. Okay, so if we know wavelength and we know frequency, right? So we know speed of wave. Okay. So amount of time require given point, right? From 0 to 12, you see, this is string, right? So this is 0, right? To 12 centimeters, so this is 12, right? So this guy moved from here to here. This guy moved from here to here, from 0, so this is y, 0 to 12 centimeter. So basically, this guy will move up, right? And then come back, move up, come back, then go down, then come back. This is one period, okay? So move up, come back, go this one, then go here, right? So kind of this, right? So move up, come equilibrium, right? Then move down, then come back. This is one period. So from here to here is 1/4 of the period. So minimum time is 4 over period, right? So you know period is 32 seconds. 32 over 4 equal to 8 seconds. That is the answer. What will be 8 seconds? 1/4 of the period. Okay, so let's move to the next one. Next one is sound 1 has intensity of 48. So this is sound 1, intensity 48 watt meter per second square. Sound 2 has the intensity level 3.5 dB, greater than the intensity level of sound. Okay, so sound 2 equal to 3.5 dB plus dB1, right? So this guy in dB is 3.5 dB greater than the intensity level of the sound 1, okay? What is the intensity of the sound 2? All right, so how to do this? We have turned to that into, so I should do this way. dB2 is 3.5 dB plus dB1, right? So we have to figure out what is dB1. dB1 equal to 10 log I1 over I0, right? So equal to 10 log 48 watt per meter square divided by 10 to the negative 2 watt per meter square. Okay, so this will be a big number. Whatever it is, right? And then you can go ahead and figure out what is. So plug whatever here into here, you figure out dB2, right? And then you do the reverse, right? So we know dB2. So now we know dB2, right? Equal to 10 log I2 I0, right? So now, because from here we figure out what's dB2, and then you can, if you know this one, and then you figure out I2. Okay, so you can go ahead and figure out I2. That is number 6. Well, keep going. In a pig calling contest, a caller produced a sound wave with an intensity level of 107. Okay, so dB. 107 dB level. How many such caller would be required to reach the pain level of 120? Okay, so how many? We don't know. Let's see, what is its intensity? Intensity, I, right? Well, so first we figure out intensity for 107 equal to 10 log I0, right? So this equal to 10 log I 10 to the negative 12, right? So you can figure out from this equation, you figure out what is intensity of this 107 dB, right? And so we call this I1, okay, I1. Then 120, so 120 equal to 10, 1 over I2, right? So this is 10 to the negative 12. And then this gave us I2 equal to 12, right? And then this is 1 watt meter square. That's what we learned in class. Okay. Then whatever it is, so I2 over I1 equal to whatever number, right? So equal to whatever number. So maybe I don't know. Let me see. 107. So what is I1? I1 equal to 10.7. Let me see. Log 10 to the power of. Okay, and then times 10 to the 10. Okay, so this is equal to 5.01 times 10 to the power of negative 2. All right, you see? This is 1 over 5.01 times 10 to the negative 2. Okay, so whatever it is, right? 0.0, basically it's 0.05. 1, so basically it's 20. It's about 20. Yeah, it's about 20. Maybe a little bit more than 20. So let's make it 21, because you have to have a integer number. Okay. All right. So that's this one. Next one. A motorcycle has and a police car are moving towards one another. Okay. The police car emit sound wave with the frequency. This is frequency. Okay, so this is original frequency and has a speed of this. Okay, so what is this? This is the source speed. We call this US, 3.2 meter per second, right? The motorcycle has a speed of this, so this is observer UO equal to 14.8 meter per second. And then they're moving towards each other, right? So go this way. They're moving towards each other. All right. And the speed of sound is V equal to 343 meter per second. What frequency does the motorcyclist hear? Okay, so equation, right? Important equation. So F frequency you get, right, equal to, so we do adjustment. V, okay. This is the speed of wave. V, right? All right, so now let's see if you plus or minus. Okay, you see, consider this guy is stationary. This guy is stationary, and this one, observer move towards, right? Move towards you, you supposed to get the more frequency, right? So plus UO. Now let's look at the source. And if you make that stationary, observer stationary, just like consider this guy stay at rest. And then this one move towards. Move towards means you get more frequency, right? More frequency, so you have to make this bottom part minus. So make it the whole thing, you get a more frequency. Okay, then F0. Okay, and well, that's it, right? So plug in. So this is a 343. And UO equal to plus 14.8, right? Is UO, and then US. Okay, source, right? 32. So 343 minus 32.2. Okay, F naught is frequency 523. Okay, that's it. Oh, you get it. This is the solution. All right. Number 9. Number 9. Here is the siren of an approaching fire truck. Fire truck. You pull over to the side of the road and stop. As the fire truck approaching, you hear a tone of, right? You see, this is a tone. So F1 equal to 460 hertz. As the truck recedes, you hear tone. Okay, F2 equal to 41. How much time will it take for the truck to get from your position? So here is your position. This is you, right? To the fire 5.0 kilometer away. Okay, this is the fire. Assume they maintain a constant speed. Okay, so you have to know speed of the fire, right? Speed of the fire truck, US, and we know speed of the sound equal to 343 meter per second. Okay, so you need to first figure this, and you are stationary, right? So this is the fire truck. Go this way, US. Meanwhile, he sent out the sound wave. All right, so this is when the truck moves towards you. That's the frequency you hear. This is the frequency you hear when it's move away, right? Okay, so we know frequency whatever frequency you hear equal to, and you are stationary, right? So you don't have to adjust the top part. So V when you move towards you, right? The bottom, so the total frequency is higher. So US and whatever frequencies is send, you don't know, right? So that is what you hear. So F1 equal to V and F naught. You don't know F naught, right? So F2 equal to V move away. So plus, move away is plus, right? F naught. Okay, so this equal to 460. This equal to 410, right? So this is 1, this is 2. You do the ratio. So so you do ratio. So ratio here is if you 1 over 2, so equal to 460 over 410, also equal to so basic ratio, right? So F cancelled, V cancelled, right? So if this 1 over this, divided by 1 over that, right? And this is V plus Vs divided by V minus Vs, okay? And V here is 343. Plug in, okay? So this is 343. So you have no, not US. It's US, right? V minus US. V 343. So this is equation to solve. One unknown here is US. Solve for US, right? And then after you solve for US, then you know this guy's speed. So the time equal to distance 5.0 kilometer divided by US. All right, so it's time. Okay. That's number 9. Number 10. Number 10 is here. A pair of in-stereo speakers is placed side by side. Okay, so this is speaker. This is a speaker, right? And side by side. 0.914 meter away. Okay, you stand directly in front of one of the speaker, 2.44. Okay, so in front, right? So this is you. And this is 2.44 meter. Okay, I did not draw that in a good proportional. Okay, use this is a v equal to 343 meter per second. At the speed of sound in air, what is the lowest frequency that will produce constructive interference? Okay, at your location. All right. So what's the condition for the constructive interference? So if the length pass difference, okay, so delta L. Okay, so this is L1, this is L2, pass length, right? Because this guy send out a sound wave, this guy send out sound wave. If the pass length difference, and you look at this is absolute sign because you're looking for the difference value, right? This equal to n lambda constructive, n plus 1, n plus half lambda. This is constructive. This is destructive. Okay, this is actually the fully constructive, fully Fu, and this is the fully destructive. All right, so that's condition. So what is L1? L1 is 2.44, right? What is L2? This is L2. L2 will be, you see, Pythagorean. Okay. All right, so because you're looking for the positive value, right? So what do we have here is, you see, path length difference equal to 2.44 plus 0.914 squared minus 2.44 equal to constructive, right? N lambda, right? Okay, so you're looking for lowest frequency. We know speed of wave equal to frequency, wavelength times frequency. If you're looking for lowest this guy, you're looking for highest this guy, right? So biggest is of wavelengths. So wavelengths equal to whatever this value here divided by n1. Okay, so if you're looking for n divided by n is an integer. So the maximum wavelength, right, equal to when n is 1. When n is 1, you have n is 1, 2, 3, right? So and when n equal to 1, you have maximum wavelength. Okay, so this basically is this value divided by 1, right? So this is maximum. So this will be your maximum wavelength. Then what is your minimum frequency? Lowest frequency, right? Lowest frequency equal to speed. Okay, speed of the sound wave is 343, so equal to 343 divided by this guy. Okay, so that is your lowest frequency to have the constructive interference here. All right, so this is number 10. Let's look at number 11. Number 11, the fundamental wavelengths for standing sound in an empty pop bottle, empty, pop bottle. So this is the bottle is this. It's a bottle, right? The fundamental wavelength, okay? So fundamental wavelength. So F1 wavelength, right? So lambda 1 equal to 0.88 meter. Use V equal to 343 meter per second. Of sound in air, what is the length of the bottle? Okay, so this is length of bottle. Length of bottle is here, right? Length of bottle. The fundamental wavelength, the lowest frequency you can have here is, you see the open part is antinode, right? So this is antinode, and this is node. Okay, so this is lowest frequency. So this end is a close, right? So this is node, this is antinode. The distance, well, you see this is if you look at the string, right? The both end is fixed. Okay, so this string, the lowest one is from this is the lowest one, right? So fixed end. This is string on a string. You see, this is node. Okay, so distance between the minimum distance between two nodes is, you see, this is one wave, right? That's one wavelength. The minimum distance between node and node is half wavelength. Okay, so this is antinode. The distance between node and the maximum distance between this node and antinode, right? The distance between node and antinode is 1/4. Okay, so this is the 1/4. So this L equal to 1/4 of the wavelength. Okay, if this is small, this is the lowest frequency, right? So you have a node, you have antinode. The distance between node and antinode is 1/4 of the wavelength. Okay, so you know this guy is, lowest one is 0.88, right? So what's the length? So length equal to 4. Length equal to, well, length equal to 1/4, right? So it's 0.88 divided by 4 equal to 0.22 meter. That is the bottle. That is the length of the bottle. What is the frequency of the third harmonic? Harmonic of this bottle. Okay, so this is a F1, right? So if we introduce one node in between, this is a node, right? So this is fundamental. So you see, this one is fundamental. Let's see, let's do a little bit. Okay, so this is node, antinode, right? So this is, right? So next one is to introduce one node. Okay, so introduce a node here, right? So just a node here. So this is also node. We introduce one, right? Just to get one. Just to squeeze one in, one node, right? So this node, and then this is node, this is antinode always here. This antinode, right? So an open part is antinode, right? So this will be like this. Okay, so this is 1/4 of wavelength. This is half wavelength. Node half wavelength, right? So the L equal to 3/4 of the wavelength, right? Not whole wavelength, but 3/4. And then wavelength, right, equal to 4, 3 length, right? So frequency equal to speed of divided by this one, right? So equal to speed for 3L, right? So equal to 3V over 4L, right? So this actually is your, okay, so let's see. What is the frequency, right? Third harmonic, the first harmonic or fundamental harmonic, right? So is F1. F1 equal to speed over lambda 1. Lambda 1 is 88, right? So equal to V 80, 0.88, right? This is the first one. So this one actually is, this actually is your third. This is one equal to 3V4L, right? So equal to 3 times V. 4L, L is 0.22, right? 4 is 0.88. And this is F1, so this is 3F1. So this will be your third harmonic. Okay, because it's 3 times of the first harmonic, fundamental harmonic. So this will be a third harmonic. And what's the frequency? Well, this is the frequency. Let me see if you have speed of wave. You see, you have 343, right? So equal to 343, 0.88. Okay, so that's the answer. Hertz, in hertz. All right, so now let's look at the last one. All right, so last one is a guitar string, 66 centimeter long. Guitar string, okay. 0.66 meter. With a standing wave that has 3 antinodes. Okay, 3 antinodes, right? Between any 2 nodes, you have antinodes. Okay, so in this case, you have to have 3 antinodes. Node here, at least you have 1 here, right? But you have 3, so you introduce 2 more. So anti, right? Between anti and anti, you have a node here, you have a node here. Okay, so this is your standing wave. You see, this is antinode, antinode, antinode. Okay, all right. So this is basically this is a standing wave. Okay, like that. Okay, so you have this, right? All right. What harmonic is this? Well, we can derive, right? So the first harmonic is this. This is the first harmonic, right? Second, then this is first harmonic. You only have 1 antinode. Then you introduce another antinode. You make the second harmonic, right? So antinode here, right? This is the second. Then you introduce another antinode, right? So you get here. So this is the first, second. This is actually the third. Let's make a 3ID. So this is third. Okay, you can see this way. What is the wavelength of the wave? Okay, so what do we have? 66 centimeter. So this is 0.66, right? So L equal to, this is the 1 wavelength, right? Half 3/2 wavelength, right? So equal to 0.66 meter. And the wavelength equal to 0.66 meter divided by 3 times 2, right? So 4 meter. That's the wavelength. Okay, because you see this is L. L equal to this 1 wavelength, right? Half, 1/2. Okay, so this relationship. All right, so that's all for this.